Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
I'm going to tell you a little bit over the next hour or so, give you an overview of collider physics. And I have this actually, it's collider physics called 101. So this lecture hall, this is the first course. So there will be quiz at the end of the lectures. So pay attention, okay? So I will start with talk about energy, importance of energy in particle physics or in physics in general. And followed by some discussions of large hadron colliders. And finally, I'll talk about detectors and the physics. However, I will not talk too much about physics because most of you probably have heard Dr. Gresham's presentation 2 weeks ago about physics at the LHC. So just like everything we do, we need tools to study natural phenomena. And the tools, to a large extent, depends on the problem you're looking at, the scales of the object you're studying. For example, if you want to look at these cells, and which have typical size of 50 microns. If you don't know the microns, it's 10 to the minus 6 meters, and which basically you can fit in about 500 or so in 1 inch. So that gives you a scale. So for that kind of scale, the microscope is good enough. You can look at, you get a sufficient magnification. However, if you want to look at deeper, like for example, look at DNAs, DNA has size of nanometers, which is 10 to the minus 9 meters. And in terms of inches, you can fit 10 million DNAs in 1 inch. So you need additional magnification, about thousands or so. You can achieve that using this electron microscope. Now, if you look at deeper, you want to look at inside the atoms, nucleus, for example. Nucleus has a size of so-called Fermi. Fermi is 10 to the minus 15. Okay? So how many nucleus can fit into the inch? You have 1 inch, you can fit in 10,000 million nuclei into 1 inch. Or if you look deeper inside the nucleus, we have protons, neutrons. What's happening in protons? And inside we know they're quarks. And in that case, the size we know sort of is smaller than 10 to the minus 18 or the autometers. So in that case, we need powerful tools, which is particle accelerators. So let me begin with talking about energy. Energy is very important, and not just for daily life. It's also very important for physics in general. So in particle physics, and we're using a unit which is spatial units called EV, or electron volt, okay? Which is the amount of energy an electron gains when it's accelerated by a 1 volt battery, okay? Take a look using example of this energized 1.5 volts batteries. And if the electrons is accelerated by this battery between 2 electrodes, and this electron gains energy 1.5 electron volts. So it's basically the voltage of the battery times the charge. Now, 1 EV, electron volts, actually turns out a very small unit in terms of carrier. So it's like 3.8 times 10 to the minus 23 carrier. This is very, very small unit. However, for electron is tiny. Everything relative. In fact, this is a huge amount of energy. The speed of electron at that energy is shown here. It's over 1 million miles per hour. Okay? So it's the enormous energy for electrons. EV is sometimes very small, and also we're using different units. We're using kilo electron volts, KeVs, which is typical energy you get from X-rays and the TVs. Televisions, these old-fashioned televisions. Our next unit, we're using MeV called mega electron volts, and this is typical energy scales of radioactivity, like in nuclear reactors, those energy levels of MeV. And next level, it's again 3 orders magnitude high. It's called GeV, giga electron volts, which is 10 to the 9th. Or next, it's tera electron volts, or TeV, 10 to the 12th. And these are the energies achieved in cosmic rays and in accelerators. Just set the scale, the speed of electron with energy 1 GeV. Practically, electron will be traveling at the speed of light, the maximum speed electron can achieve. It's 670 million miles per hour. And also, later on, we talk about the energy matter are related. 1 GeV energy also corresponds to about the mass of the proton. So the energy inside the proton mass is about 1 GeV. Now, energy is important. Energy and length are related. In 1924, a French physicist, de Broglie, as a student, he was like doctoral student. In his thesis, he proposed a theory called the particle-wave duality, which revolutionized our views of a microscopic world and also laid the foundation for quantum physics. The theory is very simple. It says particles and waves are the same thing. Particles are waves, waves are particles. Okay? So you may wonder, what are the difference between particles and waves? Well, you take a look. Particles are the things which you can see, you can touch, you can sort of locate, right? You can describe it, its positions, its velocity, its momentum. On the other hand, the wave is a phenomenon, right? If you drop like stone in a water pond, the ripple will spread out, and that's wave, right? So how they are related? Well, so de Broglie proposed that particles waves with this wavelength, we call the de Broglie wavelength, and it says lambda. Okay, using here, it's wavelength. Wavelength is the distance between two maximal perturbations. I show you in that graph. And particles are described by momentum. Momentum is p here, and momentum is defined to be mass times velocity. So, and this formula basically says, all right, rates the length. Wavelength is sets length scale, and the momentum is, you know, it represents the energy of a particle. The faster it moves, the higher the momentum, the higher energy it has. So basically it tells you h is a constant here, Planck constant. Tells you the higher the particle travels, the smaller the scale it has. So this formula sets so-called energy and the length scale. The smallest length corresponds to highest energy. Energy and temperature are, of course, related. Everybody knows, right? Phi will heat up a temperature. The temperature actually is a measure of how fast the air molecules are moving. So when air molecules move slowly, that means cold, and it corresponds to low energy. When it moves fast, means it has high energies and high temperatures. So high energy corresponds to high temperature, everyone knows. So energy and times are also related, and this is a pictorial presentation of the evolution of our universe, started from bigger bangs, and as the universe expands, and the universe cools down, right, and lowers the temperature. So currently, the universe is about 13 billion years old, and the temperature is is very low. So throughout space, the temperature is about 3 K. K here is Kelvin. It's scientific temperature unit. In this unit system, 0 represents absolute lowest possible temperature. So 3K is 3 degrees above absolute 0. Now, to set scale, the room temperature here is about 300 K. Okay? And at that temperature, the energy scale is very low. Energy is about 10 to minus 4 electron volts. And as I will discuss later, the powerful accelerators can look back in time, because by accelerating these particles to high energies, and we can look at what happens right after a Big Bang. For example, at LHC, the energy is about 1 TeV, and we can look at what happens at a fraction, tiny fraction of a second right after Big Bang, 10 to minus 13 seconds. And the temperature, we talk about 10 to 17 Kelvin. Now, energy and matters are also related, right? And everyone knows this Einstein's famous relationship, energy equals mass times the speed of light squared. And speed of light is about 300 million meters per second, or 670 million miles per hour. here's the one theory that how Einstein got that formula. He tried and error until he finds something like it, right? Now, so this formula tells us energy is matter, and matter is energy. And in fact, the energy stored in matter is enormous. If you take a look, the equivalent energy in 1 ounce of matter, 1 ounce is very small, it's about 28 grams, right? That energy is sufficient to power about 60,000 average US homes for a year. The problem is, of course, energy comes with different colors. And the question whether you can harvest, right? That's the biggest problem. So because the conservation laws prevent you harvest that energy. All right, so energy is everything. In fact, energy is the only thing in particle physics. So if you look at low energies, low temperatures, and that's atomic physics. Probably many of you heard the Ford lectures by Professor Phillips a week ago. He talked about extremely low temperatures, 10 to minus 15 Kelvin. Particle physics is another extreme. We look at extremely high temperatures. Okay, high temperature, high energies is particle physics. So the energy is the currency of the particle physics. In fact, we measure everything in the unit of energy. Distance, time, we measure in unit of energy and mass. So if energy is important, then wondering how we can gain energy, how we accelerate particles to high energies. And the principle that comes in particle acceleration. And the principle is very similar. Like a surface, ocean waves propels a surface, and the electromagnetic wave can also accelerate charged particles. Electromagnetic wave represented by the sinusoidal curve. So it will push charged particles to high energies, just like a wave pushes a surface. So that's the basic principle for particle acceleration. Now, the first particle accelerator was developed by Ernest Lawrence in 1929 at Berkeley. So this is a simple, this is a picture actually, this original particle accelerator developed. It's about 4 inches in diameter, it's very small. And it in fact accelerates electrons to 80,000 electron volts. And for this work, he was awarded a Nobel Prize in Physics in 1939. Moreover, it awarded him appearance on the cover of Times in 1937. And if you cannot read the sign there, in fact, under his name, the title says he creates and destroys. And this is basically the accelerator does, it creates and destroys. So what is a particle accelerator? And for those of you old enough to watch those old bulky televisions, that's a linear accelerator. Inside, it's a linear accelerator. If you look at the back, it's a vacuum tube, okay? And so if you look at this schematic, simple drawing here on the bottom, it has a filament which provides electrons, and then you have regions of acceleration using electrical field, and then you have regions for steering the beam or particles to the screen, okay? These are simple linear accelerators. And in modern days, of course, things slightly more complicated, but the principles are very similar. And look at these modern accelerators in circular geometry, a circular accelerator instead of linear. It essentially consists of the same thing. You have injections, which you have the source of electrons, and then you have this. You want to keep the electrons inside in orbit, so using bending magnet, using magnetic field to keep charged particles in orbit, and that's called a bending magnet on this graph. And you want to prevent the particle being blown up. You have to focus it, this focusing magnet. And then, of course, you have to have mechanism provide acceleration. And that's provided by the RF cavity called radio frequency cavity, which provides electromagnetic wave to accelerate the particles. And in circular geometry, particles move in circles. Therefore, you can have repeated kick to the electrons. So you can repeat it using those radio frequency cavities and to accelerate to high energies. So that's the advantage of the circular machine compared to linear machine. Linear machine, you have one chance, right, one shot to accelerate the particles. How does the accelerator work? And okay, first showing here these nice pictures of European synchrotron radiation facility at Grenoble in France. So all these synchrotron facilities, these Behind it, it's an electron accelerator, a circular electron accelerator. So let me show you, the Todd Johnson of Fermilab Accelerator Division actually made a video with nice demonstrations showing that how accelerator works. Let me show you, let's watch video.
Hi, I'm Todd Johnson, and I'd like to show you this little demonstrator. This is a working model of a particle accelerator that uses electric fields to accelerate a ping pong ball in a manner very similar to an actual particle accelerator. What we have is this transparent bowl shape, and there's a series of electrodes on the inside. And inside here we have just an ordinary ping pong ball that's been coated with conductive paint. And if I turn this on, this applies high voltage between these strips, just a DC high voltage. And as the ball touches one strip, it acquires the same polarity charge, so it's repelled and attracted to the next strip. And as soon as it touches that strip, it acquires the polarity of that strip. So the polarity on the ball is flipping, unlike the particles in a real particle accelerator. And then as it speeds up, it goes up the sides of the bowl. The particle accelerators that we use electric fields to accelerate the particles. The magnetic fields are used to keep the particles in a circular path. This demonstrator also uses electric fields to accelerate the ball, and there are no magnetic fields present here. The bowl itself serves the function that the magnets would serve in a real particle accelerator by keeping the ball moving past the accelerating electrodes. It's a cool thing. It's a lot of fun.
So that's actually the modern accelerator. That's how a modern accelerator works. The only thing different here, actually, we're using the magnetic field to keep a particle in orbit, and in the demo, using the balls. All right. So another thing is we talk about, right? Energy are matters, matters are energies, but not all energy can turn into matters, and because conservation laws. So it turns out that energy can be most efficiently turned into matters when two particles collide head-on. Just illustration this point here. So collision, you have two modes. One so-called fixed target mode, which you have one beam moving and your target is stationary. So in that collision, after collisions, you have forward-moving momentum, right? After fragments will move forward, and that carries away energy. And that energy cannot be turned into matter because that's in the form of momentum, because momentum conservation. However, if you have two beams collide head-on, moving in opposite direction, okay? And after collision, there's no momentum because momentum cancel, right? So all that energy can be converted into matter. And the difference is huge, showing here. This picture showing that you have one beam for the fixed target mode with 450 GeV collide with a fixed target. The available amount of energy for mass creation is only 29 GeV from this 450 GeV. Now, if you have two beams collide head-on, 450 GeV each, and the total energy, which is 900 GeV, will be available for creating new particles. Okay? You see the huge difference, 29 GeV compared to 900 GeV. So for the particle creation, it's much more efficient for you have two beams colliding head-on, and that's leads to the development of particle colliders. Now this leads me to CERN, and CERN is the European Laboratory for Nuclear Research, located outside Geneva, Switzerland, and it hosts the Large Hadron Collider called LHC, showing here as ring. You see the large ring. And you can see the rings, in fact, cross the, okay. So the French-Swiss border is shown as a dotted line there, and also a small Geneva airport. So one thing you can see here, the couple things you can see, the ring is large. In fact, it's outside CERN site. CERN site is relatively small, and the ring, in fact, crosses French-Swiss border multiple times in one turn. Okay. Another thing you notice, in fact, the ring actually goes through villages. You see the several villages there, and which is, you have particle accelerator goes through underneath your house, which is probably unlikely in this country. CERN, besides hosting this large accelerator, is also known for, anyone knows other development at CERN? There's one other major development at CERN. Everyone should know. What is it?
World Wide Web.
That's right. So CERN, the World Wide Web, was developed at the late 80s at CERN. And the intent at that time, of course, is not for commercial application. It's because there's people around the world working at CERN, how you can share the information, how can you share the data with people around the world, okay? Distribute the information, okay? Access the information. And that was CERN was originally proposed to do. And now these days, right, it's not just particle physics information, we share everything, all the information. All right, CERN had these larger hadron colliders, and let's take a look and let's show the video explain what large hadron collider is.
The Large Hadron Collider is a journey of discovery, a global undertaking to explore the mysteries of nature at both the smallest scale of the quantum world and at the largest scale of the cosmos. In order to imagine the challenge, consider what might be the world's most powerful search engine. It is a project sited on the border between Switzerland and France at CERN, the European Laboratory for Particle Physics. It is a ring of superconducting magnets 17 miles long, buried deep underground. It accelerates two intense beams of protons at nearly the speed of light. The two beams are brought into violent collision with energy densities that have not existed since instances after the Big Bang. The beams collide in the center of large experiments consisting of complex arrays of particle detectors. Deep in the heart of the detectors, protons from each beam interact. New particles are produced. They are recorded by precision detectors, generating an enormous volume of data, more than 1 billion petabytes over the lifetime of an experiment. Scientists search this data for the answers to their queries.
All right, so that's what a larger hadron collider is for, and looking for the new particles, looking for new physics beyond the physics we know. So next, I will go over some of the key components of the larger hadron colliders. So larger hadron collider itself is an accelerator, right? It's huge accelerators. And basically inside the accelerator, you have two circular proton beams brought into collisions. And the proton beams are kept inside the super cold vacuums. So there are 4 interaction points, and each interaction point hosting one experiment. And LHC cannot operate alone. In fact, it requires some smaller accelerators to feed the proton beams. For example, start with PS at the bottom here. PS stands for the proton synchrotron, which accelerates protons to 28 GeV. And after that, PS feeds the protons into SPS. SPS stands for super proton synchrotron, which accelerates proton to 450 GeV. And then SPS acting as a feed to the LHC. And the LHC eventually will accelerate the protons to 7 TeV or 7,000 GeV. So it's really complex of the machine involved. And particles are actually in stages of energies. Now let's look at some numbers. And LHC, it's a circular machine. Its circumference is about 17 miles. It's underground, between 50 to 100 meters underground. The machine is, of course, is flat, horizontal, and the surface is not, because Geneva actually is 3 sides of Geneva is mountains. And it weighs about 38,000 metric tons. And the beam energy right now, it's operating at 3.5 TeV or 3,500 GeV. Eventually, we're going to double the energy to 7 TeV. So at that energy, basically, the proton travels practically at the speed of light. And magnetic field used to keep the beam in orbit is 8.3 Tesla. Now, you probably don't know much about this unit here. In fact, 8.3 Tesla is close to our technical limit to build a magnetic field of such volume, such complexity, larger scale. So this is the most limiting factor for the machine. How high to accelerate particle, the energy is really determined by this magnetic field, because in order to keep the particle in the same orbit, you need a stronger magnetic field at high energies. Energy per beam is about 400 megajoules, and just say scale 1 megajoules melts 2 kilogram copper. And this is talk about energy. We're not talking about the energy spread over the larger space. We're talking about energy concentrated in tiny, tiny space volume. The power consumption of the machine is once running 120 megawatts. To set scale, Arbor consumes about 190 megawatts in 2008. So it's really consuming more than half of the energy of the city of Arbor. So as any machines, actually there are 3 major components. One is dipole magnets. These are the magnets which keep the particles in orbit. Okay? A charged particle inside the magnetic field will move in circular motion. All right? And that radius of the motion depends on energy. The higher energy, the larger radius, if you keep the magnetic field constant. If you keep the orbit as constant, you'll have to increase magnetic field at high energies. And in fact, most of the real estate in a machine is occupied by these dipole magnets, keep particles in orbit. Next major components called your quadrupole magnet, and these are magnets to keep to focus the beam, so to prevent the beam blowing up. And typically, it's made up from like 4 solenoid, shown here. And finally, you have these radio frequency cavities, which actually provide the acceleration to the particles, and using electromagnetic wave. So around the LHC rings, there are 4 acceleration points. Now, when 2 protons beam collide, they reach temperatures 10 to the 17 degrees. And of course, this is for very small volume, otherwise we're in big trouble. So for comparison, the sun, on the sun's surface, our sun, temperature is by 5,000 degree Kelvin. In the core of sun, which where nuclear fusion takes place, and the temperature is about 10 million degrees, right? So look at this, the temperature the LHC creates at over small volume is 10 orders of magnitude higher than the temperature inside sun. And in terms of a condition it creates, which is very similar to what happens right after the Big Bang, 10 to minus 13 seconds right after the Big Bang. And it really is a hot spot in our current universe. Now, to reach that, actually, you need to start with cold, right? As I mentioned earlier, LHC beams are constrained in orbit by magnetic field. And to create that magnetic field, we need current. This magnetic field are created by electromagnets. And we need enormous current to create the magnetic field. So in order to minimize power consumption, actually make it practical, you have to use a superconductor magnet, because the current is just too enormous to using conventional magnet. So we're using superconducting electromagnets, which operates at liquid helium temperatures, 1.9 Kelvin, okay, which is 1.9 degree above absolute zero. Or in Fahrenheit, it's negative 457 degrees below zero. The amount of mass involved to cool down, warm up is huge. It's like 38,000 tons. So it literally takes about a month to cool the whole thing down or to warm things up. You cannot do it overnight because the amount of energy involved is just enormous. And it requires about 10,000 tons the liquid nitrogen, which keep it cooled down to about 70 degrees, and using a liquid helium to cool down to 4 K and further to 1.9 K. So it is the world's largest refrigerator. Now, it also has the world's largest instrument, the precision instrument. So once you have the accelerator, right, and you want to look at collisions, you have to build a detector. You need an instrument to look at the collisions. So large scientific instruments are built to track particles over micron precision. Micron is 10 to the minus 6 meters. Precision over like 50-meter length. And typically, detector has about 100 million electronic channels. Now, these detectors actually not much different from digital camera, okay, except in size. So, but these detectors, right, a camera, you take a picture per second kind of thing, but this detector has the capability to take pictures, 40 million pictures per second. So it's very high rate over large volumes. And they are not only sensitive to light, like cameras sensitive to light, and this detector are sensitive to all kinds of radiations. Light, electrons, hadrons, protons, neutrinos. So LHC collides protons. So the question is, normally collide protons. LHC can also collide the heavy nuclei called heavy ions. So what are protons? We know the protons. Protons are constituents of a nucleus. Inside nucleus, they are neutrons, protons. And protons are small, on the order of Fermi, 10 to minus 15 meters. But they are not, they still have size. They still have structures. Whereas we know, the proton, in fact, inside mainly consists of 3 quarks. Made from 3 quarks, we call valence quarks. Okay? And the proton has size about 1,000th size of a normal atom. But that's a simpler picture. In fact, inside protons is much more complicated. Besides the 3 so-called valence quarks, the vacuum, quantum physics tells us the particles can create and destroy constantly inside vacuum. So inside it, protons, in fact, you have the so-called C quarks, are constant pairs constantly create and destroy. Okay? And at any given time, you not only see those 3 valence quarks, you can see those C quarks typically have low energies created by vacuum. You can see gluons. Those quarks are bound together by gluons. Gluons are the so-called force carriers of strong interactions. In fact, if you look at the proton energy, how much proton energy is carried by valence quark. And in fact, valence quark here, in general, quark carries only half of the proton energy. And the other half of the proton energy is carried by gluons. So when a proton collides with another proton, we are not really looking at a proton collides with a proton. In fact, what happens is it's constituent. It's collisions between quarks and gluons inside the protons. Okay? And proton itself just provides a means to transport those particles. The collision actually really happens between quarks and gluons. So what really happens inside the collision, we have no control. So what we see is, after collision, we see big special particles. So our job is try to figure out what's happening. So do an investigation. Looking backward, look at all the traces, find out what caused that. So what really happens in a collision depends on physics. And that's depending on the probability the process happens is described by cross-section, one of the quantity, physics quantity. Just remember this is proportional to the probability. So every different physics process have a different cross-section, therefore they have a different probability for happening. And for a given collisions, we can never for sure say what exactly happens. We can only say for certain probability, this process looks like that, like a particular process. And this quantum mechanics. Quantum mechanics, everything is uncertain. You describe things by probability. Okay? So the process with larger cross-section have larger probability to happen. And by definition, those processes are less interesting, right? If things happen often, people have studied before, that's not interesting. So we're always looking for small probability events, processes people haven't studied before. They might be new physics. So those processes typically have smaller cross-section. Showing here, like in the bottom here on this graph, these are like Higgs production, small cross-sections. These are most interesting. The plot showing here is the cross-section as a function of the energy. And in log scale, in vertical log scale, basically every major tick is the order of magnitude change. Okay, so we look at a process with small cross-section like Higgs production. So once the collision happens, it's very hot, right? And the particle fragments moving apart from the collision point. And so when quarks gluon produced, they're flying apart and they're rapidly cooling down. When they move apart, they're rapidly cooling down. Okay, so a process called fragmentation. So suppose you have quark-antiquark pair produced, and they are connected by color force, by strong interaction. Color force can be modeled by like spring. So as quark-antiquark move apart, spring will stretch, right? When you stretch a spring, the energy stored in the spring increases because force increases. At some point, the energy stored in the spring is high enough to create a particle, the quark-antiquark from vacuum. So the spring breaks, right? Just like it breaks, create another pair of quark-antiquark. And this process will continue until it's cold enough that no new particles or quarks can produce. So what you get is you get these fragments of particles as the particle moving away from the interaction point. So in detector, it looks like this. Suppose you have a production of 2 quarks and gluon, okay? And each will fly apart. So in the detector, what you see is basically a flow of particles in those 3 directions, okay? All right, so once the collision happens, we have to build the instrument to look at it. And at LHC, there are 4 major detectors. One of those is ATLAS detectors, and for which Michigan is involved. Now, this is a picture of ATLAS detector during installation. You look at the end views. So what you see here is, its scale is about, the height is about like 25 meters high. What you see here, you see these 8 toroid magnetic field for the muon detectors. Inside, you cannot see here. Inside here, the inner detector calorimeters, and these are toroid magnets. Now, every detector actually looks very similar, all right? They maybe have different technologies, but the principle is very similar. Here is schematic views of the ATLAS detectors, and start from interaction point at the bottom. So close to interaction point, typically you have track detectors, which made from silicon detectors or gas detectors, which tracks charged particles, sensitive to charged particles. And the charged particle bends inside magnetic field. By measured bending, you can determine its momentum. Now, outside trackers, you will have, outside trackers, you have calorimeters, and which calorimeters are sensitive to both neutral and charged particles. And finally, in outer layer, you have muon detectors. Okay, quickly, so trackers, let's talk about magnetic trackers. So magnetic spectrometer is a device. In fact, actually, I should stop here. The particle detector, in fact, have 2 kinds of detector, 2 classes of detector. One is tracking detector, which is sensitive to charged particle, which is using magnetic field to bend the charged particle. Another is called calorimeter. Calorimeter is based on the fact that particles will create big splash when they hit the material. So I've described those. So if you look at magnetic trackers, it's a device basically for measuring momentum of charged particles by passing them through the magnetic field. Here are the pictures, so-called old days bubble chamber pictures. You see those tracks, those are charged particles, and they bend inside magnetic field, right? The curvature of bending depends on the momentum. So by measuring the curvature bending, you can determine particle momentum. So these trackings, you need a magnetic field. For example, showing here this ATLAS solenoid under construction. Right? Solenoid is you have these wires winding around this cylindrical surface, and the current will create a magnetic field, showing here in the bottom, the cartoon show here. Magnetic field will be in the axial direction of the solenoid. ATLAS solenoid has a magnetic field about 2 Tesla. So that's a tracking detector. Tracking detector basically based on this bending of charged particle inside a magnetic field, which is tracking detector in general is not sensitive to neutral particles. There's another type of detector called calorimeter. In particle physics, calorimeters detect for measuring energies of both charged and neutral particles. It's based on the fact that when you have energetic particles hitting heavy materials, it's going to create a big splash, okay, because of interactions. And there are 2 kinds of interactions. One called hadronic interaction, which is due to strong interactions. And another type of interaction is electromagnetic interaction, which is due to electrical charges. So electromagnetic interaction typically is narrow, and hadron interaction typically wide. And then you build detectors, try to catch those energy depositors. So there's 2 types of detectors. One homogeneous, you basically contain this cascade during the interaction particle into one homogeneous detectors. Or you can sampling. The second part is sampling. You don't record all the energy. You sample the energy. And the energy you sample is proportional to the incoming particle energies. So you determine the energy of incoming particles from these cascade particles. These are the 2 basic principles of detectors. Now I just quickly show some ATLAS detectors. And this is ATLAS silicon detectors under construction. And this for the trackers, and the ATLAS calorimeters being installed and ready for installation. And ATLAS muon detectors. Here is actually from real data. You're using the so-called similar to X-ray tomography. So basically, you look at the photons. Photons are just the high-energy X-rays, and look at where they come from. And you can see a material because the photon interact with materials, and you can see where the interaction happens. You can see the material inside the detector, just like doing X-ray. You see the nice structures of materials of detectors. So protons, they collide at a rate of 40 megahertz. and which means 40 million collisions per second. But we have no capability to record all the information for all these collisions, right? Our technology is not advanced enough because the amount of data created per second is huge, right? 40 million hertz per second. And so also, there's no reason to record everything because most of interaction correspond to a process with larger cross-section, which had been studied before, right? So we're only interested in process with small cross-section, small probability. So the challenge now is try to decide which event to record, which event to throw away. And you have to make a decision very fast, right? You talk about this 40 million collision per second. So actually, between two collisions, the time you have 25 nanoseconds. Of course, you can buffer some information. That usually give you like a microsecond time for decision. Okay? So you have to build sophisticated electronics to do this. And typically, we build a so-called multi-level trigger system, right? So level 1, so-called first level trigger is based on purely hardware. Just look at pulse height information, electronics, okay? And that provide us about affect 500 reduction to 75 kilohertz. And next level is the so-called firmware. Firmware is a mixture of hardware and the software in between. All right, software is just computing farm. So that's give us another like affect 25 reduction to 3 kilohertz. And the final level is software level. It's just you have like 1,000 computing farms to process event to decide what to record. So at the end, we record 200 hertz, 200 events per second, okay, instead of 40 million hertz. Hertz is like one per second, right? Even for that, so each event has size of about 300 megabytes, okay, each event. So if we record 200 events per second, in a year, we will have about 3 petabytes raw data. This is just raw data from the collisions. Of course, when we process them, we double the data size, right? We process and analyze. So what's petabyte? Petabytes 10 to 15 bytes, so there are 15 zeros. Okay, that's a huge amount of data. Now, so just set scale, the data recorded by each LHC experiment, if you try to fill with conventional DVDs, it's 2 million DVDs a year. All right? If you talk about CD typically have 700 megabytes capacity. It's like 15 million CDs. And so to analyze those data is a challenge. And we have collaborators scattered around the world. So we have hundreds of computers of CPUs around the world and have to analyze those data. So the challenge is to try to integrate those together so everyone can have equal rights to the data. So that's how the so-called computing grid comes in. Computing grid computing just like power grid, right? So when you get a power, right, you plug in, the power comes delivered to this classroom, to your home through a power grid. You don't know where the power comes from, just plug in, you get the power, right? Computing grid, the concept is the same. You want to do some calculation, right? You want to compute the power. You just submit to the grid. You don't know where the job runs. You just, at the end, you get the results back, right? That's the same concept. So we have collaborated, we have this showing the pictures, basically illustrating of computer farms distributed around the world, and they have, all come to CERN, like get data from CERN, distributed to the other side, and people have access data from, either central side or satellite side, and that's leading to development of the grid computing. So let's watch a video about computing.
The challenge of our search for new discoveries, the challenge of finding a handful of interesting particle interactions in our sample of billions of trillions, requires vast computational resources and some innovative new techniques. Large processor farms process data in nearly real time in order to sift through tens of thousands of particle interactions per second to pick the 100 or 200 interactions that we can afford to store. Even with this reduction, our detectors are so fine-grained that each experiment may store about 15 petabytes of data per year. This data volume is equivalent to a stack of about 15 million CDs, or a stack of about 12 miles high. In order to amass the required computational resources needed to reconstruct and analyze our data, CERN and its experiments have assembled the worldwide LHC Computing Grid. This is an association of 60 or so computer centers around the world. Data is recorded at CERN, and it is then distributed to clouds of geographically clustered centers for further processing and analysis.
All right, so the computing challenge is enormous, right? I mean, there's a reason why the World Wide Web was developed at CERN, because that was one step towards the meet that challenge, distribute the information around the world. Okay? All right, so once we have a detector, okay, we'll look at event. Just showing you a couple of event pictures. Here showing a so-called clean event. Now this is after reconstruction, okay? And this event happens very at small rate. So this is actually reconstructed as a TT bar candidate, the top quark event. And was top decaying to WBs, and B quark actually can be reconstructed, showing a top left. You can see those zooming in the interaction vertex. You see tracks come from, you see most tracks come from the interaction point. And then you see, you can see here in the B quarks, B quark decays away from the interaction point. B quark has a certain lifetime. So these are clean TT bar candidates. Or you can look at some events are very massive. Showing here, it's a heavy ion events. Basically, you have big splash. Now this is not a PP collision. This is heavy ion. Heavy ion corresponds to the heavy nucleus, lead nucleus collisions. And what you have enormous energy. You have enormous track produced. And you have all kind of energy deposits. So our job is to try to make sense what happens, do some detective work, trace back, look at the clues for a particular physics process. All right, let me now talk about a little bit about physics. Spend the last 10 minutes on physics. And the physics or particle physics is really described by a theory called standard model. And standard model, probably many of you heard it many times, I suppose. I'm not going over. It's nice summarized by this poster. Everything you want to know is in this poster, except you cannot read. Standard model is very successful, but there's only one problem. Like any physics, the physics, in fact, is based on symmetry, right? The people probably heard about momentum conservation. Momentum conservation is because there's translational symmetry. What does that mean? That means if you do experiment at that point, or you do experiment over there, you move your apparatus, physics does not change. That's translational symmetry leads to momentum conservation. So physics is based on symmetry. Particle physics is also based on symmetry, but it's more complicated internal symmetries. So symmetry is the foundation of standard model. However, there's one problem. Particle mass, we know particle has mass, particle has weight, and that breaks the symmetry. So in one hand, you have one very successful model based on symmetry, but on the other hand, experimental evidence you have which breaks that symmetry. Okay? So there's this problem. Now, this problem was nicely solved by Peter Higgs. So in 1964, Peter Higgs proposed an elegant solution, which basically says this. Initially, the particle has no mass. Particle has zero mass, so the symmetry is preserved. Particle gain mass because they interact with another particle called Higgs Boson. And so this process is called spontaneous symmetry breaking. So in other words, it introduced a new particle called Higgs Boson. And this Higgs Boson is different from any other particles. It is responsible for mass for all other particles. In other words, responsible for the weight for all other particles. Okay? So Higgs Boson is very unique. Right? It interacts with other particles, give mass to other particles. Right? So it's responsible for all the mass in your universe. The mass in this room, because the mass of the, most mass actually containing proton neutrons. And proton neutrons gain the mass from the ground energy inside and quark mass inside. Higgs has a unique role in that, but one of the can respond for a lot of things, but don't blame Higgs for your other mass. All right, so the good news. The theory actually describes data in great precisions. Theory is very successful with this with Higgs boson. However, we have no trace about Higgs. We haven't seen direct evidence of Higgs. That's the problem. That's one of the major problems in particle physics. So in fact, the search for Higgs boson is one of the major physics goals of the LHC. Okay? And so in fact, Michigan is heavily involved in particle Higgs searches, and we hope certainly in the next few years we can have something to report. And we have to look at everywhere, just like this cartoon says, right? So another problem is dark matter problem. And it's really embarrassing, okay, how little we know about our own universe, right? And you probably heard about the dark matter, dark energies. And universe, if you look at the energy content of the universe, only 4% of energy content is so-called invisible matter, the matter we can see. Matter emits light, all right? And so 23% are matters in matter which we cannot see, and they don't emit light. And then even worse, 73% are so-called in the form of dark energies. Now, dark here is word for ignorance, right? It's really trying to mask it. If something you don't know, you call it dark, okay? So LHC, in fact, have the potential to resolve dark matter mystery. And so if your dark matters produce, dark matter could be a particle due to particles. And those particles, they do not interact with detectors because they're dark, so you don't see them. So what happens, but those particles still carry momentum. And the momentum is conserved, so you can look at the visible particles and try to infer the existence of dark matter particles. So a typical signature is look like this. If you look at this event, this is from simulation. You can see events is one-sided in one side. This looks like apparently imbalance. Something is missing, recoiling against that event. And this is indication of possible dark matter candidates. All right, so that's only two physics topics I'm going to talk about. There's a lot of other physics topics LHCs can do, and people talk about many extra dimensions and many black holes or string theory or whatever. And probably you heard that, but time is running out. As I said, this is class 101, so we will do some quiz. All right, are you ready? Okay. So first question. So it's class quiz. First question, have you learned anything today? Oh, I'm wasting time. So you get 2 points for yes, 0 for nothing. And the rest of the question, where was the World Wide Web born? You should know this. What does LHC stand for? Good. What Einstein theory is mentioned in this talk? Special relativity, great. What's the maximum speed of a particle can achieve? Speed of light, great. Approximately how many protons are in your body? 5 points. 5 points? All right, so last one, you get bonus points for attending, okay? So here's the answer keys. You know everything except how many protons you have. It's 10 to 28 approximately. For 100 person who weighs 150 pounds. Okay, it's an enormous number of protons. And you have about equal number of neutrons in your body. All right, so how many, you recorded your scores, all right? So what's your grade? What's your grade? So remember that if you did really well, you get the 8 points above. I suggest you do a career change. And our chair is not here, but our dean is here. Talk to him, okay? If you did the average, don't quit your day job yet. Continue at the park first, all right? And for those of you get a 2 or below 2, unfortunately I cannot help. And you got this. But that's not the end of the world. That's not the end of the world. With that, I just want to say LHC is running and we're analyzing data. Stay tuned. Thank you for coming.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.